We are now ready to begin the second presentation for this session. So please welcome James Wyke, who will be presenting on Zero Access Command and Control Communications.
Good afternoon, everyone. Welcome to Back Channels and Bitcoins. My name is James Wyke. I'm a senior threat researcher with SOPHOS in the UK. This presentation aims to expose some of the less well-known aspects of the Zero Access botnet, which is one of the most widespread threats on the internet. In particular, we're going to look at the technical reasons for Zero Access's longevity and success by examining several ways that the authors actively attempt to mislead and deceive the security and AV community. So let's start by looking at the agenda for the presentation. We'll begin with a brief introduction into exactly what Zero Access is, before taking a look at some of the interesting aspects that occur during installation. We'll then take a look at a few of the downloaded modules, in particular the tracker module, the click fraud module, and the Bitcoin mining module. We'll then try and make some estimations about how much money the botnet might be earning before finishing with a conclusion. So a brief recap of exactly what Zero Access is. So Zero Access is effectively a downloading bot that connects into a custom peer-to-peer network to download binary module files. These modules effectively carry out the payload of the botnet, which is the monetizing activity that gets performed on the endpoint. So the main component of Zero Access and the peer-to-peer protocol itself have undergone several revisions over time. In particular, they've moved away from a kernel-mode architecture where they used kernel-level rootkit techniques to hide various aspects of the activity towards a more user-mode approach that's more easy to maintain and more adaptable and can be employed across architectures and on newer versions of Windows. The peer-to-peer protocol itself has also undergone several revisions. In particular, it's moved away from a purely TCP model to a more UDP and TCP combined model where most of the protocol takes place over UDP, but file transfers are carried out with TCP. Throughout both revisions of the peer-to-peer protocol, one thing has remained, and that's that it's extremely noisy. Anyone with a packet sniffer on an infected machine quickly notices a large amount of very suspicious data. So this is a very brief overview of the peer-to-peer protocol. So each node connects to all the other nodes it knows about, and the live node responds back with information. So the current version of the protocol sends out GET requests to peer addresses, and each peer responds with a RET-L command, which contains a subset of the peers that that node knows about and a list of the files that it has on its endpoint. And so each infected machine will send out a GET request at the rate of 1 per second, which, if the bot's are live for a 24-hour period, will result in over 80,000 packets of data a day. Added to this, the protocol uses fixed port numbers, which means that the traffic itself is very easy to identify and detect. But it seems that the authors intentionally use, to a degree, the noise of the protocol to mask certain other aspects of the command and control infrastructure that's used to administer the botnet. So let's look at what happens at installation. So essentially, each dropper phones home with certain information about the infected machine during installation. There are two techniques used. The first is an HTTP GET request, and the second is by encoding a packet of data and sending it out on UDP port 53. So it's designed to look like DNS traffic. The purpose of this data is to feed the affiliate program, which is used to distribute Zero Access. So another request that happens at installation is that the bot will send out a HTTP request to a GeoIP service to retrieve the country code of the externally facing IP address of the infected machine. This is important to the affiliate program because it pays out primarily based on the location of the infected machine. The US, for example, will pay out far more than any other country in the affiliate program. So this is what the GeoIP lookup looks like. It's a simple GET request. The server responds with some JavaScript, which is then passed by the bot to retrieve the country code of the infected machine. So currently, a URL on maxmind.com is being used, which is a legitimate GeoIP service, although previously they were using a URL on fling.com. So So a closer look at the HTTP GET request. So this is made to a legitimate seeming web counter URL. It's legitimate seeming in the sense that you can visit the domain, you can sign up for a web counter yourself, put it on your website, and it will act as a web counter should do. It will display a number, and every time a hit happens, the number is incremented. However, there's certain information encoded into the headers of the GET request, specifically in the user agent field, about the infected machine, which means that the Zero Access authors must have access to some extent to the web server logs on the web counter domain. So there's certain relationship between the owners of the web counter and the Zero Access authors. They may even be the same people. So multiple GET requests are made, and each time a numeric value in the URL is modified based on the path of execution through the dropper that happens on the endpoint. So for example, if the dropper is executed as administrator, a different numeric value is added to the string, and we get a different hit counter is incremented with each hit. So this means that the authors can count the total installs for each stage of execution that the dropper takes. So this is what that GET request looks like. There are 3 highlighted values in the user agent field. The first is an operating system version value. The second is a country code. In this case, it's BG for Bulgaria. And the third denotes the architecture of the infected machine, this time x86, but it could be x64. We then see the sequence of each HTTP GET request with the numeric value modified each time, indicating at what stage of execution the path took. And then underneath, there's a capture of one of the hit counters at a particular point in time. So because the hit counter functions correctly, we can visit that URL and effectively count the total number of installs at any particular point in time. And if we plot this over a longer period, then we might be able to estimate the infection rate that Zero Access is managing to achieve. So earlier in the year, there was one portion of the Zero Access botnet that was performing this technique. So over a 17-day period, the current counter was measured, and even though this is only one portion of Zero Access, it's still some very high figures. So it starts out at around 300,000, and after 17 days, it's already got over 1 million. So if we look at just the number of new installs on a day-by-day basis, we can see that just one portion of the botnet is managing to get in between 60 and 20,000 new installs every day. So the average number over that period is actually 49,000. And again, it's only one portion of the botnet. In 2012, when all Zero Access droppers, and therefore all portions of the Zero Access botnet, were performing this technique, the same thing was done, and over a 3-month period, the average number of new installs on a day-by-day basis was 140,000 every day. So the other technique used to send information back at installation is by sending an encrypted packet on UDP port 53. So this data is designed to look like DNS data. As you can see from the packet capture, Wireshark will interpret this as malformed or corrupt data. And the addresses used to send the data back to, which are hard-coded into the dropper, have changed relatively little over time. The servers have not been brought down, so this technique seems to be relatively successful at not being noticed. So let's take a look at the module files that are downloaded from the peer-to-peer network, starting with the tracker module. This module is downloaded by all 4 of the Zero Access botnets, both 32-bit and 64-bit, and its purpose is to send information back about the infected machine to centralized servers in 50-minute intervals. The main purpose of this data is to ensure that when new droppers are pushed out onto the internet, the initial seed peer address list that those droppers carry with them will be very accurate in terms of live peers. They have very accurate information on which peers are live at one particular point in time, and they can ensure that when new droppers are executed, they're very likely to connect successfully into the peer-to-peer network and download the module files. So the addresses that this data is sent to are retrieved dynamically from another module downloaded through the peer-to-peer network, a data module. And again, we see that the IP address in particular changes relatively little over time, meaning that the technique is being missed. And the port number, although it can be changed by the new module being seeded into the network, hasn't changed at all, and it's been consistently port 123. So because this data is sent over UDP, this looks like network traffic protocol data. So the actual information encoded into this packet, two important fields here are the affiliate ID and the bot ID. These remain consistent across a reboot because the dropper encodes them into the NTFS extended attribute of the U directory, which is where the Zero Access module files are stored. So the tracker module will always send back the same affiliate ID and the same bot ID for any one infected machine. So this is what that data looks like in Wireshark. You can see it interprets it as corrupt NTP data, and only one packet every 15 minutes is very easily missed in a busy PCAP file, and very easy to dismiss as OS, as normal activity generated by the OS, and not by the malware itself. So now let's take a look at the click fraud module. So this is downloaded by two of the Zero Access botnets, the 32-bit version running on port 16464, and the 64-bit version running on port 16465. So this module has been very actively maintained, going through a number of revisions, but most of the changes center around the interplay between client and server to retrieve the click fraud URLs and process them. Common to each revision has been that the initiator of the click fraud process is an outbound HTTP request. And also common to revisions is the technique of spoofing the host field in that HTTP request. Now, for a while, a version that was in the network was using a domain generation algorithm to generate that host value. So no DNS request was actually ever made because it's a spoofed value, but it was sort of used as a kind of semi-authentication where if you made the GET request but didn't include the correct generated host, no click fraud data was returned by the server. But it's not always obvious that the host is not being genuinely used. So members of the security community started to pre-generate the future domains and pre-register them in an attempt to sinkhole this part of the botnet, when in fact it has no effect whatsoever. Another technique used by this module has been to employ decoy URLs into the data returned from the server. So for a while, after the HTTP GET request is made, the server responded with some encoded data, which after decoding contained a series of URLs, which appear to form part of the future click fraud process, perhaps as URLs to be clicked or referrer URLs. But they don't actually appear anywhere in the subsequent click fraud exchange. So it looks like they have no purpose. That is until they're visited with a web browser, as it appeared that the IP address that visited that URL subsequently no longer received genuine click fraud data from the web server. So reinfecting a machine and connecting out through the same IP address, the click fraud component no longer worked properly. So it appears that these URLs were intentionally embedded in the code, as the only people who were going to be seeing them were people analyzing the data exchange. They deobfuscated the data, and they got curious about the URLs. So they're very likely to be AV companies or security researchers, so they were immediately added to a blacklist, and the click fraud process no longer worked off that machine. Let's move on to the Bitcoin mining module. So the two botnets that do not download the main click fraud module have been downloading a Bitcoin mining module. So this is a modification of the UFAsoft Bitcoin miner, which is an open source miner that can be downloaded freely on the internet. It connects with an HTTP post request to a push-pull type mining server, which then responds with JSON data, which is processed by the client and executed as a mining task. So this is what the post request looks like. It's very easy to identify. It's on a non-standard port, and there's clear headers such as the X mining extensions header, and in the user agent field, the name of the miner is included. An Nginx host then responds with mining tasks to be carried out. So in the early part of 2013, the Bitcoin currency started making headlines across the world as it went through an extreme boom in the exchange rate. There were financial problems in the Eurozone and in Cyprus in particular. People were moving their money out of traditional bank accounts into electronic currency in an attempt to stop the government from seizing those funds. This had some interesting effects on the Bitcoin mining module in that the module first appeared into the network on the 12th of May 2012 and didn't receive an update for over 9 months. This is very unusual for Zero Access modules, as every other module downloaded through the network underwent several revisions in this time period. And when an update did finally occur, it actually disabled the module. So a new version with the same file name is released into the network, it's downloaded by each peer, and overwrites the existing module. But the new version doesn't have any code, so it has no functionality, and it effectively just disables the mining ability of the module. So this happened just before the price boom in Bitcoin exchange rate. As the price went up to near $100, another update is issued into the network, this time re-enabling the mining functionality. This stays in the network for about a month until it is again disabled. So looking at this on a timeline, you can see in February, when the price is around about $25, the module is first disabled. As the price nears $100, a new module is released, which again re-enables the mining functionality. The price goes up past $200, has a crash, but it's still above 100 when again the miner is disabled. And that's the way things stand now. The Bitcoin mining functionality of Zero Access does no longer exist. So why was the Bitcoin miner disabled? Obviously, we can't know for sure, but we can make some educated guesses. Possibly the currency was seen as too unstable by the Zero Access authors. When the price is going up to that extent and down again, it's very difficult to estimate from one day to the next how much an infected machine is worth. Another possible reason is that it was either too difficult to cash out mined Bitcoins, or in fact that the Bitcoin mining functionality was not really working very well, and not many Bitcoins were successfully being mined. A machine that's performing Bitcoin mining tends to use a lot of resources and is therefore very noticeable from a user's point of view. Therefore, they're probably going to reboot it a lot, and it might be that it's not very frequent that coins actually get successfully mined. A third reason is that with the Bitcoin currency gaining so much attention throughout the world, so too does a botnet that is known for mining Bitcoins. So perhaps when the profile of the botnet rises, there's a lot of unwanted attention from law enforcement, AV companies, and security companies. So maybe the Zero Access authors decided that Bitcoin wasn't worth the trouble anymore. So the final module we're going to look at is more of a general purpose module, but it's primarily used for click fraud. So it makes an outbound HTTP request, and a server responds with tasks for the module to perform. This can be arbitrary file download and execute, but currently it's only being used for click fraud. So again, with the outbound HTTP request, the authors decide to spoof the host field. The way this module does it is slightly more subtle than the previous module in that an initial DNS request is made to the fake domain, but the response is ignored, and the real address that the HTTP request is sent to is retrieved from the data module, which is downloaded through the peer-to-peer network. So because there's initial DNS request, it's very obvious to miss the fact that that address is not really being used when you're looking at a PCAP file. What complicates this is that if you're using an intercepting proxy to analyze the traffic, the proxy itself will intercept the request, make another DNS request, and it will send it out to the actual address received from DNS rather than address supplied by Zero Access. This looks even worse when some of those fake domains are sinkholed by security researchers, so that when you're analyzing it in a proxy, it looks very much like this component of Zero Access has successfully been sinkholed, when in fact it hasn't. It's only the fake domain. So this is the list of fixed fake domains that's embedded into the module. They look random, but they're fixed, and once you have the list, it's very easy to know what they are. And this is the ignored DNS request. So when the DNS request initially goes out, before the response is received, a new TCP connection is initiated, and an HTTP GET request is made to a different address which we eventually receive from the DNS request. And we can see that the responses differ when the server is sinkhole and when it's genuine. The sinkhole server will respond with a very nice X sinkhole header, whereas that doesn't appear in the genuine response. And the server is different as well. It's Apache as opposed to Nginx. So how much money might the Zero Access botnet be earning? Let's start by trying to estimate how much Bitcoin might be earning. So previous work has put the possible number of Bitcoin mining nodes at around 500,000. If we give them a reasonably generous estimate of an average hash rate of 4 megahash per second, this gives the total capacity of the mining pool at 2,000 gigahash per second. So this is a reasonable sized mining pool. It's not one of the biggest on the internet, but nevertheless, it's pretty good size. So at various rates of exchange for Bitcoin, we can see that at $10 per Bitcoin, the botnet might be earning over $600 a day. At 200, it's more like 12,000 a day. But we know that this module was disabled, so it seems very unlikely that Zero Access was managing to earn anywhere near these sorts of figures in terms of Bitcoin mining, possibly for the reasons we outlined earlier. So when we try and estimate how much money ClickFraud might be earning, again, we can only make some estimations. This depends very much on how often the fraudulent clicks that are executed by the module end up in money being attributed to the Zero Access authors. And this in turn depends on how good the anti-fraud departments are in the various ad networks that are being defrauded. So these two previous works go into detail about how to try and estimate how much a botnet the size of Zero Access can earn through ClickFraud. And it's a reasonable estimate to say that between $90,000 and $200,000 a day could be made through ClickFraud. So finally, what conclusions can we draw? Well, we know that Zero Access is a very resilient and long-lasting botnet. It's been around for several years and is showing no signs whatsoever of dying out. We know it's extremely widespread. There's an enormous number of new installs happening a day. Upwards of 100,000 new installations every day means that this is extremely widespread botnet. We know that the authors are very adaptable. They very closely monitor publications from the security industry. They've moved away from a kernel-mode architecture to allow it to be more updatable, more maintainable in user mode. They've changed the peer-to-peer protocol to make it more resistant to sinkholing attempts. They frequently use misdirection in the form of pointless domain generation algorithms, decoy URLs, fake DNS requests, to try and commit resources into areas that they shouldn't be, that won't have any effect on destroying the Zero Access botnet. We've seen they like to masquerade important network traffic as legitimate seeming network data. So they try and hide it as NTP data, as DNS data, embed information in HTTP requests. And we've seen they move away from more high-profile money-earning schemes like Bitcoin to less noticeable schemes like ClickFraud in an attempt to try and stay under the radar. So that concludes the presentation. Thank you very much for listening. I think we have some time for questions.
We have time for a couple questions, so is there any question in the room? No question? I have a small one for you, James. When you're describing the command and control protocol, you showed that one counter is returned to the bot when it's reporting. Why do you think that the malware operator would disclose this information to any infected system?
What was the question again, sorry?
When the bot is reporting after installation, it reports to a counter. And the command and control server returns the counter of the number of bots that are active. Why do you think that the operator is disclosing this information?
I think because it makes it seem less innocuous. So it seems like it's just a normal web request from the endpoint to a normal web counter. It doesn't seem like it's associated with Zero Access. I think that's the main reason for it. But it's also something that this technique tends to be used sometimes. For example, it was used all the time last year, started to be used again by part of the botnet this year, and now they've dropped that technique because people are starting to notice what they're doing.
You have one more question?
Hi, James. The news over the last couple of days that Symantec have been supposedly cleaned up a quarter of all infections. What do you think this will have done for Zero Access?
So yeah, apparently 500,000 infected machines have been sinkholed. So anything that inconveniences the malware authors is fine by me. But when you've got upwards of 100,000 new installations every day, it doesn't take very long before you regain those sinkhole nodes. They also updated the peer-to-peer protocol so that you can no longer sinkhole new nodes. And certainly in our statistics, I've seen over the last month or so a large spike in new zero-access droppers as they're seeking to rapidly replace the sinkholed nodes. So I think we're basically pretty much back to where we were before the sinkholing happened.
James, do you think there is a correlation between the price and exchange rate for bitcoins and how many botnets are actually involved in mining?
It's a good question. To be honest, I don't think the mining aspect has a huge impact on the price of Bitcoin. It's much more to do with some extremely suspicious trading activity, where if you watch the price against certain block trades that happen, you can see that you can almost predict the rises and falls. Certainly when there was going through big peaks and big troughs, you could almost sort of spot the pattern where it was going to peak, and you could see lots and lots of suspicious activity sort of trying to manipulate the price so that people can just drop their coins, buy them again cheap, and then sell them again. I think the mining functionality from botnets represents a relatively small portion of the amount of Bitcoin mining that's going on. I'm not sure that it really works that well as a concept, because when you look at the really large public mining pools on the internet, the capacity they have is enormous, and the people performing the mining have systems that are vastly different to the kind of systems that get infected by normal malware. The hash capacity of a normal machine is pretty minuscule. It's orders of magnitude more massive when you're actually building a system designed to do Bitcoin mining.
Great. So thank you again for this presentation.
Thank you.